Hi everyone. Can you please confirm if I'm audible? Okay, please confirm it quickly if I'm audible, and then we will be starting file system. So we have already started the file system in last video, but today we will be solving more questions, right? Great. Can you please confirm me? Okay, so let's get started. Now let me just quickly revise that what we have already seen, right? And before that, let me quickly introduce myself. I'm Sachin. I have done my masters from Indian Institute of Science, and I'm co-founder and instructor at GoClasses. And after my masters, I have done I have been at Amazon for more than 1 year. I worked as an applied scientist there. I've also got all India rank 33 there. Okay, so now let's start with our topic, which is file system, right? Good. So as we talked about the file system yesterday, that like what are the file system, what are the things that we are going to study, and what are the methods that we have in the file system, right? So let me quickly just revisit them, and then we will be solving more questions. So what is a file? File is a data in some format, right? I mean, it could be a PDF or JPG, but anyway, it is just zero ones. So our objective is that we want to store this file on the disk, right? So, I mean, from this implementation, what we are expecting to provide a way to store a file, provide a way to name file, provide a way to store the metadata, provide a way to have the fast retrieval and so on, right? So basically, this is our objective. Like this, all the things are coming under the file system. So we want to do all sort of these things. Okay. Now, what is a file and how does the extensions look like? So these are the few extensions, some popular extensions that I have taken from a book, and that book is Tenenbaum. You might see it here. So let me just show you. So yeah, the source of this image is Tenenbaum book. So from there, I have taken some of the this screenshot. There they have listed some of the popular extensions that we have for the file system, right? For the files. Now, what are the operations that you can do on the files? These are the different operations that you can do on the files. Okay. So I think this is what we have already seen. And in this lecture, what we are going to see, like there are two things. One is that how to store the file, and another one is that what is the hardware. Right? Hardware means that how disk or sectors are organized, what is the rotation latency, what is the seek time latency, and these things. So this we will not study. This we are going to study, or we are going to revisit in COA or DBMS. But today we are going to just study the OS part of it. OS part means that what I mean, how we are basically going to store those files, right? So there are few methods that we discussed yesterday also. So it is as good as saying that it is very analogous of saying that you have a file, and or maybe you have some luggage, or maybe you have some box that you want to store in a room that is full of almirahs, right? So this box is your file, and your room is your disk. So this box is your file, and this room is your disk, right? Now obviously, like what you want to do, you want to have the fast retrieval and so on. Like there are few objectives that you have in your mind. Now we are going to study few methods, and once these few methods are covered, then we will just see that how these modern operating systems like Windows, Mac OS, and these operating systems are implementing these few methods, right? So they may not implement them directly, which means that they may not implement them as it is. They may implement some part of method one, some part of method two, like that, right? So they will be implementing like that, and I mean they may not implement is one to one. They like Windows will be implementing, let's suppose 80% of method one, 10% of method two, and so on, right? Okay. Now what is a file and directory, and these things we have already talked about. So therefore I'm just moving to the slide which we have not talked about. If you are completely new, then I will just suggest you to watch the previous lecture, or half of the previous lecture, where I talked about the file implementation, right? Okay. So we talked about this linked and all, but quickly let me just revise that what are these 3+3 approaches. So I will call them 3 approaches or 3+3. I mean, doesn't matter. So these 3 approaches are there, but these are having one small variation. So that's why I can call it 3+3 methods, right? Or just call it 3 methods. Doesn't matter. So first is contiguous. It is very easy. I mean, your file will be stored in the contiguous. That's the one way to implement it. And one drawback of this is you can easily see that internal fragmentation is there, right? So there you have the internal fragmentation. And also you have the external fragmentation. I mean, external fragmentation, internal fragmentation, both are possible. Reason being is that for the external fragmentation, I mean, you will say that if you want to store a file that is requiring, let's suppose, these three blocks, then you cannot store that file, right? So that's why it is an external fragmentation. So that's why there is one variation that is called extent based variation or extent based allocation. In this variation, what we do, we allow, I mean, we are not too much strict about the contiguous. We are saying that okay, some part of contiguous is available here, some part of contiguous is available here, so let's just allot them, right? So these regions are called extent. Now you cannot say that we are not contiguous. I mean, we want to be as much as contiguous as possible. Okay, so this is just a little flexibility we are giving. It doesn't mean that we can misuse this flexibility. Misuse in the sense that you cannot use. I mean, you should not be using the arbitrary block, like one block here, one block here, one block here. No, I mean, you should be contiguous as much as possible. Otherwise, it will be just like a linked list. That is what we don't want, right? So we want as much as contiguous possible. So this is called extent based. And then this is the linked list based that you know. And the one of the variation which is very important variation. I mean, in the file system, there are only two things which are important: the like the index allocation and the fat. Okay, so fat is very important variation of your linked allocation, right? So in this fat, what we do, we have one table. I mean, see, earlier also, as I told you in the last lecture, so earlier also you had this linked list. Now also we have this linked list, but the only difference is that we are going to have some extra table. And how does this extra table help us? Still we are doing the pointer chasing, but now in the main memory, right? That's what we talked about yesterday. Do you remember it? Harish, Akash, Sumant, I hope you remember it, right? So we talked about it yesterday that that we are going to have something extra, but now in the main memory. Now we will be doing in the main memory. Okay. Now there are two operations that we do. One is read, another one is write. Read means that if you are just bringing something from the main memory, it is called read. If you are going to write that also, that's called write. Sometimes you need to do just one of them. Sometimes you need to do just two of them. I mean, two of them. Can you give me any example where only read is required? Can you give me any example where you only read? Okay. So let's have an example. Example where only read is enough. Only read is required. I mean, there could be many examples. One of the example is this fat table, right? I mean, fat table. In case of fat table, also we just bring that and we do not write it back. So this is just one example. You can say, I mean, there could be many example, obviously. So just in case of fat table, also we only read it, right? We just bring the table in the main memory. We do not modify the table, and we do not need to write that table. Since we have not modified that, that's why only read is enough, right? And can you give me an example? Only write. Example where we do only write operation. Can you give me some example where we do only write operation? Maybe you have, if you have seen the question that we have solved yesterday, the dirty page, right? The page is dirty. Then in that case, we do not need to read anything. We just write that page wherever it is required, right? We just write that page if that is dirty page. So I'm just giving you one example, and maybe somewhere you need read and write. Can you give me an example? Yeah, maybe if you want to modify some part of it, right? Some part in file. Then what you will do? You will bring that part of the file in the main memory. You will. It means that you have read it, right? So see, the third example that I'm going to talk about is basically. So let me write that example. Example when both are required. Both operations are required. What is that example? Can anyone guess it? So yeah, that's very easy example. What is that example? You can say that you are going to modify some part of the file, right? if you want to modify some data in file, then obviously you will bring, then step one is what? You will bring that file, bring file to main memory, right? This is your step one. And what is the step two? So this is main memory. If it is not visible, just keep it main memory. Okay. So this is step one. And what could be the step two? Step two is that make some changes and write it back to the disk. Step two, make changes and write it back to disk. So there could be any number of examples where the read and write both are required and like that, right? Yes, Akash, that is correct. So that is correct. I mean, there could be many examples. I'm just giving you one or two examples, right? Okay. Now, I hope you understood that here, what is the difference between here and earlier? Earlier, if I want to, let's suppose earlier, if I want to go to this particular block, right? Let's suppose earlier, if I want to go to the last block, then what I have to do? I have to basically read it, right? Why I have to read it? Just to know that what is the next block. Then I have to read it, then I have to read it, then I have to read it, then I have to read it. And then finally, after 1, 2, 3, 4, 5 reads, I will get to know what is the address of this. But using fat, how many reads you are doing? Can anyone tell me using fat how many reads you are doing? Just bringing this fat in the main memory, which means only one read operation you are doing here, right? Only one read operation. So that's the benefit of this fat. I hope you understood that why we are using the fat, right? That's very important to understand. Okay. Now let's talk about a few questions related to fat. So suppose that they are saying the entry size is 16 bits. It means what? Let's suppose in the fat table, okay, fat table, each entry that you are making is a 16 bit. See, generally here what we store the block number, right? So they are saying the block number is 16 bits. I mean the entry size is 16 bit, need not to be just block number, maybe block number plus something else. But yeah, so let me just call it entry, okay? Let me just call it entry size. So that is basically 16 bits. Most probably it should be 2 power 16 blocks should be there, but yeah, that is okay. This is 16 bits. What is the maximum size of the fat? Okay. See, what they are saying is that if 16 bit is the entry size, if they are, let's suppose this, all of this is just a block number. Can you tell me number of blocks? Number of blocks. If 16 bit is a block number, the number of blocks must be 2 power 16. Right, in the fat, if you remember, then all of the entries there is one entry corresponding to one block. So that's why how many entries will be there? 2 power 16 entries will be there. 2 power 16, yeah, 2 power 16 entries. Why? Reason being is that there is one entry corresponding to every block, and maximum that could be say 2 power 16 blocks, right? Because 16 is the entry size. So that's why this is 2 power 16 entries are there. And then what they are asking, what is the maximum size of this fat? So you can say 2 power 16 entries could be there. Okay, in terms of entries you can say this is the maximum size. Given that 512, they have given that 512 byte block, so the block size is given to us. What is the maximum size of the file system? FS means file system, right? So given that they are saying the block size is given to us is 512 bytes, right? And this is then what does this mean? If one block is of 512 bytes, and there could be 2 power 16 blocks, and one block could be 512 bytes, which means 2 power 9 bytes. So it is 2 power 20 into 2 power 5 bytes, which is 32 MB, which means your complete disk, right? So it maximum size of this file system, it means that complete disk, right? Your complete disk could be of 30 MB only, 32 MB only. Why? Because you just have 2 power 16 blocks, you just have 2 power 16 blocks, and and one block size is also given to us 512 bytes, right? So yeah, so that is why you can find out the disk size. Let me know if that is okay to everyone. Okay. Yes. So I hope that's fine. Now, now this is one optional read that if you want, you can read it. That I've taken from the Galvin. So this is one optional read from Galvin. If you want, you can read it. Otherwise, you can skip it. Right? Okay. Now let's solve this question. This question I have taken from IIT Bombay. Uh, I think this question is not 100% visible. So let's solve this question. What they are saying is that consider a FAT file system, which means they are using the FAT, and where the disk is divided into m byte blocks. So the block size is given to us is m byte, right? M bytes. And every FAT entry can store n bit block number. So the block numbers is n bit. It means number of blocks are also given. Number of blocks is 2 power n. What is the maximum size of the disk partition that can be managed by the FAT design? So what is the maximum size of file system? It could be 2 power n number of blocks into the block size, which is 2 power n, which is 2 power n into m, right? So that's also very easy question. I hope you can do it. Let me know if that is fine. Okay. So I hope that is understood. What is the size of FAT? Okay, that's a good question. What is the size of FAT? So let me just, I think you are asking here. So the FAT is basically having how many entries? I think it is having 2 power 16 entries, because there are 2 power 16 blocks. So 2 power 16 entries it has, right? And each entry is of 16 bits. Each entry is of 16 bits, which means 2 bytes. So I think this is the size of FAT table, which is 2 power uh, 2 power 17 bytes, right? 2 power 17 bytes. This is the size of your FAT table. Okay. So now let's move to the next question. So I hope you understood this question. This question I have taken from IIT Bombay website. Okay, there is one assignment of IIT Bombay. From there I have taken this question. Now let's move to the next question. Yeah, this is the answer. This question has been asked in GATE. Let's just solve this question. What they are saying: a FAT, which is a file allocation table based file system, is being used, and total overhead of each entry is in the FAT is 4 bytes in the size. So they are saying each entry size, right? Entry size is given to us is 4 bytes. Given a 100 into 10 power 6 bytes disk. So disk size, the complete disk size is also given to us 10 is power 8 bytes. Okay. Now what they are asking, on which data the block size is given to us is 10 is power 3 bytes, right? So block size is also given 10 is power 3 bytes. What is the maximum size of the file that can be stored? So they are asking that what could be the maximum size of the file that can be stored. Do you want to try this question? See, number of entries are given to us, right? So they are saying that, yeah, oh sorry, we need to calculate the number of entries. They have given the number of blocks. How many blocks you have? So let's just calculate the size of the FAT. So maybe let me go to the next page. Okay. So there are few details that are given to us, and they are asking few other details. So let's write each detail one by one. What is given to us? They have given the block size, right? They have given the block size is 10 is power 3. Okay, I will not solve this question. I will just write all the things that are already given, and I will just convince you that what they are asking. Now, can you tell me if file size is also given? I mean, file system size or the disk size. Okay, so they are saying the disk size is also given to us, which is 10 is power 8. Now, can you tell me number of blocks in a disk? Can you tell me this number? What it will be? I think it will be 10 to the power 8 upon 10 to the power 3. These many blocks will be there in the disk. Do you all agree? Right? And now, please let me know if there is any problem here. Right? So if these are the blocks, then it means these are the entries in the FAT, right? So number of entries in FAT is equal to number of blocks, which is equal to, I mean, that's what we want to calculate, which is basically equal to number of blocks, right? And which is equal to, can anyone give me the answer? Which is equal to 10 to the power 5. So these are the entries in the block. So okay, let's not worry about what they are asking. Let's just first tell me that what is the size of FAT. So now you know number of entries in the FAT, and then can you now tell me what is the size of FAT? One entry size is also given to me, right? So entry size is also given to me, which is 4 bytes. Now tell me the size of FAT. It will be 4 into 10 to the power 5, right? So basically it was given, and then similarly it was given. We just calculated the size of FAT, which is number of entries into the size per entry. So this is the size of FAT. And what is the size of disk? It is 10 to the power 8, right? Now see, you in the disk, what you need to store, at least you need to store the FAT, you need to store the FAT table, and this is just a metadata. I mean, this is some extra data that you are storing. Apart from this FAT table, you need to store the files, right? You need to store the files, maybe multiple files, maybe just one file, it depends on you. Now they are saying that what is the space left for the file. If the total disk size is given to us is 10 to the power 8, and this is what we have just calculated is 4 into 10 to the power 5. Now the like space left for the file is space left for a file. I mean, there could be multiple files, but they are saying what is the maximum size of the file that you can store. So you can store this much as a maximum size of the file, right? So if you take, I think 10 to the power 5 common, that will be 10 to the power 5 into 10 to the power 3 minus 4, which is 10 to the power 5 into 996, isn't it? So this much bytes you can store, this much big file you can store. Like that's what they're asking, right? So they are saying that maximum size of the file that can be stored in the unit of 10 to the power 6 bytes, which means unit of 10 to the power 6 byte means you need to divide by 10 to the power 6. So if you divide this number by 10 to the power 6, then you will be getting your answer. Can you do it? So let's just divide this number by 10 to the power 6. So if you divide it by 10 to the power 6, then I think 99.6 is your answer, right? I mean, there won't be any unit because they are saying that these are the bytes. 10 to the power 6 itself is a bytes, so byte to byte will get cancelled out. So 99.6 is your answer. Let me know if it is understood to everyone or there is any doubt here, right? I hope that is understood. So what they're asking is that what is the maximum size of the file you can store? Okay, they will be asking the same question in case of index allocation also. There also we will be solving with some other method, but yeah, this is just one question that they have asked in case of FAT, but they can ask the similar question that what is the maximum size of file you can store in case of index allocation that we are going to study next. So now can you recall me that what we have studied till now? We have studied the contiguous. Can anyone quickly tell me what is the variation of the contiguous that we have studied? That was the extent based. Then we have studied linked, right? Linked. And what is the variation of it? This variation is very popular, which is FAT, right? Which is FAT. Now we are going to study the next method, which is called indexed method. Indexed. Okay. Let's just see that method. And then we will see multi-level indexing also, which is the variation of it. Multi-level indexing. So this is what we have covered, and now we are going to see this. Let me know if there is any doubt till this point. Okay. Now let's see this index allocation. Let's see what they are asking. Linked allocation solve the external fragmentation, right? I mean, there is no external fragmentation obviously in the linked allocation. However, the linked allocation cannot support the efficient direct access. Okay, so there are problems in the linked allocation because you cannot directly access any of the file, right? Efficient direct access. Yeah, I agree that FAT is available, but still, I mean, that's not very much convenient. So with the FAT, you can directly access that. I completely agree. I mean, FAT is a very good way. See here, this FAT. Sorry. Yeah. So this FAT is one of the very good way to implement the file system. Reason being is that here you are basically bringing all of this in just one file, all of the pointers in just one disk or just one sector, right? And then you can bring that in the main memory and then you can do it. But it's still not very convenient. So index is very convenient. Let's just see this index allocation. What it says that what you do, so like in linked list, everyone was connected like this, right? Everyone was connected like this. So they are saying that what you do, you allocate anywhere, you allocate your data anywhere, and all of the pointers are just at one place, which is, I mean, in the metadata, which is in inode. Right? Earlier, the inode was having just one pointer, right? If you recall, then earlier the inode, this inode was having just one pointer, right? Just one pointer to the front block. But if you are going to bring, if you are going to say that okay, all of these pointers are in this inode, then it is called index allocation, right? If you are going to bring all of these pointers in the inode, then it's called index allocation. That's what we are going to study now. Is this clear to everyone that what is this index allocation? We are just going to bring all of these pointers in the inode itself, right? So wherever it is pointing, I mean, this all of these pointers are in this inode. Now what we are going to do, I mean, we are going to store all of these blocks in just in just this inode, right? So these are the block pointers. So just a second. These are the block pointers that we have, and all of these block pointers are in the inode. Okay, this is the inode that you have. Now see, this is file A, and file A is stored at 3 places, and similarly there is a file B that is stored at 3 other places, or two or three other places, and that is fine. I mean, you can store something like this, and you can say that okay, this is the inode of the file A, this is the inode of the file B. Okay. So what is the benefit of this particular scheme is that this is sequential and random access is very easy. I mean, if you want to access some sequential data after this also you want to access, then you know that after this where to go, right? And if you want to just randomly access some data, if you want to just randomly access, you can directly go there. But there is a disadvantage of this, which is that the mapping table requires a large chunk of contiguous space. Same problem we were trying to solve earlier. So basically, I mean, there is a table that you need, and if you want to store all of the pointers, then this table can grow larger, right? So see here, what may so happen that you can say that okay, in your table, let's suppose you fix your inode size, right? Okay, suppose your inode size is going to be, it can, let's suppose, hold 10 pointers. Then what you will say, you will say that okay, if we are going to hold 10 pointers, then the maximum size of file will be 10 blocks only, right? Maximum size of the file will be 10 blocks only. Is this okay to everyone? Now now it might not be much desirable, which means what we want, sometimes we want the maximum size of the file to be bigger. So in this case, what we need to do, we need to increase the inode size, right? I mean, if we want the size of the file bigger, if we want bigger size for file, then we need to increment or increase, basically we need to increase inode size, right? But that's also not a very good idea. I mean, if we are keeping the very big inode, then there are also small files. I mean, there are not only big files. Let's suppose that just because of the one file you made your inode size very big, then there are many entries in the inode which are empty, right? There are many entries in the inode which are empty. So what we want the inode size to be smaller. I mean, see, the desired thing is this. What we want is this. We want the inode size to be smaller. At the same time, what we want? At the same time, we want the file size to be bigger. Right? Is this possible to have both of this word? The best of both of this word? Let me know. So the answer is yes, that is possible, and that is done using the multi-level indexing, right? That is done using the multi-level index. See here. So what we will do? Okay. So earlier that this was the picture. Earlier this was the picture where many entries got remain empty. But now what we will do? We will not have very big inode. We will say that okay. I will keep few of the inodes such that in this I will this. I mean I will keep the inode such that the few of the entries will directly point to my block, and few of the entry will point to something which will point to the blocks, which means this one entry itself can point to multiple blocks. Earlier one entry was pointing to just one block, but now one entry can point to the multiple blocks. So what is the benefit of it? The benefit is that if you are having a bigger size of file, then you can basically have a indirect pointer. So see here it works like this. I mean, see, it is a revision, so that's why I might be going little faster. So I'm just expecting that you know all of this thing. That's why I'm just going little faster, right? So we are using the indirect pointers here. How? There are some direct pointers also, but it is pointing to something. It is pointing to this block, and this block is basically the same thing. And this block is actually pointing to this block, this block, this block, like that, right? So we are going to have the indirect pointers in this case. See, here there could be the direct pointers like this, but there will be the indirect pointers, which means if this is singly indirect, it will point to a block, which will point to some blocks, and if it doubly indirect, it will point to something, it will point to something, and this will point to the blocks, like that, right? Very easy. Now I think we can do some questions based on it, because they have asked some I mean many questions, I think, based on this kind of a scheme. So let's just solve some questions. Okay. Yeah. So let's just solve these questions. What they are saying: consider a file system with 2048 byte blocks, and okay, block size is given to us, which is 2048. Let me write BS, block size 2048 bytes. Okay, and 32-bit disk. 32-bit disk means there are 2 power 32 blocks. Basically there are 2 power 32 addresses that are possible in this disk. It means 2 power 32, not bytes, it is blocks basically. Okay, this is the disk size. And file block pointers, 32-bit disk and file block pointers. Okay, each file has 12 direct pointers, which means if it is having 12 direct pointers, then these will point to 12 blocks. So that's why into just block size, plus singly indirect. So if single indirect will point to one block, that will point to many blocks. So in one block, how many pointers I can hold? Let me just calculate it first. In one block, number of pointers. So one block size is 2048 upon what is the pointer size? It is 32-bit, right? It is 32-bit, so that's why you will say, I mean, that's a 2 power 32 blocks. So basically, you can just uniquely distinguish using the 32 bits. So this is the byte, I think, and 32 bits means 4 bytes, right? So this is 512. So 512 pointers you can hold, right? So you will say that okay, if this is singly indirect, if it is singly indirect, then it is going to point to something which is actually pointing to 512 data blocks, right? 512 blocks. So if 12 direct blocks plus 512, because of 512 blocks because of the single indirect, and because of the doubly indirect and one doubly and one triply, okay, because of the doubly it will be 512 and each is pointing to 512 plus 512 over q. So these many blocks you can hold, and if you want to convert that to a bytes, then you can multiply by 2048, right? These many bytes will be there. Okay, so I think you got it. So see here, this is, yeah, into 2 into 3 into this 4 into 3. So first one is 12, yeah, 12, right? So yeah, so 2 power 11 means they have multiplied it later. So this is the size that they are saying. This is the maximum size of the file that you can have. Okay, this is the maximum size of the file you can have. This question has been asked in GATE many times. Okay, many times, not just 1 or 2 times. I think 3 or 4 times they have asked. How large of the disk can be? The disk can be of 2 power 32, right? 2 power 32 blocks, which means it will be 2 power 43 bytes, which is 8 terabytes. Okay, so 32-bit disk means 2 power 32 blocks. I hope that is fine to everyone. Let me know if you have any doubt. Okay, now let's see this question. This question has been asked in one of the assignment at IIT Bombay that I've taken. So what they're saying is that consider a file system with 512 byte blocks. Assume an inode that is having holds a n direct data blocks. Okay, n direct. So n directly you will be pointing plus a pointer to a singly indirect, right? So see, 512 byte blocks. Block size is given to us is 512, and then what is the number of bits, I mean number of bits that you require for each block, so that you can find out the number of pointers. Okay, single indirect block can hold pointer to m other data blocks, and direct blocks they are saying, and a pointer to singly indirect blocks. Okay, they have given that to us, that singly indirect can hold a pointer to m things. So singly indirect, which means it will be having, it can it so there will be one singly indirect, it means that can hold a pointer to m data blocks. So this is m data blocks and each one is having size n. So that's why this is m into n size of data that you can point just using the singly indirect. Now what they are asking, what is the maximum size of the file that can be supported by this inode system? Okay, sorry, this is m into 512, right? M into 512, and this is n into 512. I think it will be 512 will be common, n plus n, right? Why? Because this m is because that there are because of 1 I just don't have 1, I have m, right? I have m here, and n I have already, n I have at the singly level, I mean at the first level, and then there is one pointer which is singly indirect that is pointing to m data blocks. So because of this I have m, because of this I have n, and the block size is 512. So that's why this is the answer, right? Okay, so I hope you are getting. Let me know if there is any doubt. R is asking, what if we delete some link from inode, then how to manage that empty space? I did not get your question. I mean, there must be some management. If what you are saying, please think about it. I mean, whatever you are saying must be. I mean, there must be a way. You are saying that if we are deleting this block, how to manage the free block? Okay, there are some strategies that are called free bit and all, right? So we are not going to study them now, and these strategies are called free bit and all, like we have already talked about that in our course, right? So if you recall from the course lectures, then you can recall it. Now let's solve this question. What they're saying, that there is a large files which have we have seen different file system, right? Okay, so till now we have seen three file systems. One is contiguous, one is linked, another one is indexed. We have seen the three file system that supportedly fairly large files. Now let's see how large a file in the various file system can support. So yeah, this question is very important in the sense like it covers all the variations. So till now we have seen 3 plus 3, 6 methods. This question is basically asking file size in all of this, almost all of these 6 methods, right? So let's just see. I mean, we have calculated the file size in fat, I think. We have calculated the file size in index. We have not calculated the file size in extent based and all, and these contiguous regions. So let's just see if this question can cover that kind of possibility also. Okay. So assume for all the questions in this part that file block is 4 KB. So block size is given to us, which is 4 KB. So your solution is in unsimplified form for the parser credit. Okay, consider a really simple file system that is called direct FS, where each inode only has 10 direct pointers, each of which can point to a single block. Direct pointers are 32-bit in size. What is the maximum size? I think you can easily calculate this, right? That's easy one. Okay, consider a file system called extent FS with construct called an extent. The extents have the pointer, the base address and the length. Assume that the length field is 8 bits. Assuming that inode has exactly one extent, okay, you have exactly one extent, okay, and then this, you have the start of this, and then you have the length of this. Length of this could be at most 256 because the 8 bits you can have. Then what they are saying, what is the maximum size of this extent that you can have? So what is the maximum size that you can store? Just think about it. Okay, just try to solve this question, and meanwhile, let me just wait for you. I hope that's fine, right? See, the only catch here is that you have 255 length. What does it mean? So if you are representing 8 bits, then I mean, if you are having 8 bits, it means that the length could be at most 255. 255 what? 255 bits, 255 bytes, 255 blocks, what? So they have given that length in blocks, right? So if you're writing 5 in the field, if you're writing 5, then it means you have 5 blocks, like that, right? If you're writing 255, then it means you have 255 blocks. So basically the length can vary. If there is a 8 bits, then the length can vary from, so this is 256, which means the length can vary from 0 to 255 basically, right? That can vary from 0 to 255, and that is in the blocks. If you're writing 5, it means 5 blocks. You're writing 255, it means 255 blocks. So the extent size, the one extent size, right? So it is given to us. So that's why we are writing it like this. So you can say the maximum size of any extent will be 255 blocks. Right? Minimum size could be 0. It is ranging from 0 to 255. Now that is why you will say that your file size, since there is just one extent, so your file size could be 255 into whatever is your block size. Block size is 4 KB, so into 4 KB. So 255 into 4 KB is your answer, right? I hope you got it. Now let's just see this third question. Consider file system that uses direct pointer. Okay, I think you can do it, right? Direct and direct pointer, that's what we have already done. Now let's go here. Consider compact file system that try to save as much as possible within the inode. Thus, to point one file, it stores only a single 32-bit pointer to the first block. However, blocks within the compact FS store 4092 bytes of user data and 32-bit next field. much like a linked list. So basically they are forming a linked list. What they are saying, that in this inode you just have a pointer to one block, and then they are saying this block is actually pointing to something, right? So thus the points to files, it store only the single 32-bit pointer. This pointer size is 32-bit, okay, and then whatever it is pointing to, that will point to something. However, the blocks within the complex stores 4092 bytes of data. So here you have some data which is 4092 bytes. This data is 4092 bytes, and then what do you have? And the 32-bit pointer, right? 32-bit pointer, 32-bit, it is given in the bit, and thus can point to the subsequent block or null, indicating there is no more data. First, draw a picture of the inode, a field that is 10 kilobytes in size, inode, and the file that is 10 kilobytes. Okay, they have given that file size is 10 kilobytes. That's very interesting. See here. So this is the current scenario, and the file size is 10 kilobytes. Now, can you tell me how many blocks I will be having? See, this is 4092, which is 2 power 10 is 1024, 2 power 11 is 2048, 2 power 12 is 4092, right? This is 2 power 12 bytes, and then you also have 32 bits, which is basically how many bytes? 32 bits is basically 4 bytes, right? So this much is your size of one block that you have, and you have to have 10 kb of the file. If there is 10 kb of the file, anyway, let me not add this 4 because that's not required for this calculation. If you have 10 kb of the file, then how many blocks you will be having? In one block you can only store 2 power 12 bytes, right? I mean, this much byte of data you can store. So this is 10 into 2 power 10 bytes. So number of blocks that are needed for you, number of blocks, 10 into 2 power 10 upon 2 power 12. So I think this is 10 upon 4, which is, I mean, you need to take it seal, because if there is any more data left, then you have to store in other block. So there are 3 blocks that you will be needing. Let me know if that is fine to everyone, right? You will be needing 3 blocks, and that's what they're asking. They're asking to draw the picture. So I hope that is fine to everyone, right? So there is one inode. In that inode, you are storing 3 blocks. Sorry, in the inode you are storing the first block to pointer to the first block, and then you are storing total 3 blocks. So the complete picture will look like this. See, this is the complete picture, where you are having one inode that is pointing to something, and then ultimately you are going to have three blocks. Now what they are asking is that what is the maximum size of this maximum file size? So what could be the maximum file size here? How many blocks you can keep on pointing to? What is the size of the disk? Okay. Um, yeah, see here, 32-bit pointer is given to me, right? So if 32-bit pointer is there, then there could be 2 power 32. There could be 2 power 32 blocks, right? So number of data blocks will be 2 power 32. Is this okay to everyone? Right? Number of data blocks are 2 power 32, and then one block is having 4092 bytes. Okay. This is 4092, like 2 power 12 is 4096 basically. But anyway, if you do the same calculation, you will be getting this 3 only. Okay. So yeah, the block size in this block, you are going to have 4092 plus 4. You are going to have 4096. So number of blocks is this, and block size is 4096. Why? Because these are this how I calculated this 2 power 32, because 32-bit pointer is given to me. That's why I have calculated it, and block size is given to me in this way: 4092 plus 4. 4092 plus 4 which is 4096, which is 2 power 12. So number of blocks given to me, block size is given to me. Now can you calculate? The disk size? So disk size will be 2 power 32 into 2 power 12, which is 2 power 44 bytes. This is your this much is your big the disk size. Now they are asking what is the maximum file size. Okay, what is the maximum file size that you can store? So what do you think should be the answer? See, in any block, you are storing a pointer, right? So number of blocks are 2 power 32. It means number of pointers you are storing, number of pointers you are storing 2 power 32. Each pointer take 4 bytes. So total pointer size, total just pointer size, right? Pointers size, I mean whatever you are extra storing, that is pointer, right? Into 4. So that's why 2 power 34, right? 2 power 34 bytes. So this is the total pointer size. And what is the total disk size? Is 2 power 44. So that's why you need to subtract 2 power 44 minus 2 power 34. So this much you have wasted, right? You have wasted in just pointers. So this much big file you can actually store. You can, this is the data left, I mean space left for the file. Let me know if that is fine to everyone. Yes, Sumant, that is correct. Right. So these are the number of blocks that you have, which means these are the number of pointers. So basically, if you want to store a file, then you need to subtract the space that you have wasted because of the pointers. Okay. Now let's do the next question. So these are the answers here. See, these are the answers. Okay. Now let's do the question that has been asked in GATE. Now, what they're asking, in an index allocation scheme of blocks to a file, okay, in index allocation scheme, the maximum possible size of the file depends on what? Can you solve this question? The maximum possible size of the file will depend on, just try solving this question. See, what is the formula to calculate the maximum possible size? You will say the maximum possible size is number of pointers that it can hold into a block size. I mean, let's suppose it can hold 5 pointers. Then I mean, currently I'm just focusing on the direct pointers. Okay, direct pointers. Number of direct pointers can hold into the block size, isn't it? So the maximum possible file size depends on these two factors: number of direct pointers and the block size. Now, okay. I hope you understood this. Now let's just see that. I mean, to what factor this block size and the number of direct pointers depends on, right? So basically, what you will be doing, see, you will be storing your file somewhere, something like this. There will be inode. Okay, let's suppose only one inode. Let's suppose you are just storing one file, and then this will be the file. This is the metadata and this is the real file. So let's just let's just answer this question. Size of the blocks, okay, and the size of the addresses of the blocks. Does this depend on the size of the blocks? Yes, definitely. And the size of the addresses of the blocks. Yeah, it depends on these two. Definitely it depends on these two. Because see, I mean, basically the number of pointers depends on that, what is the size of the pointer. If the pointer size is less, the number of pointers will be more, right? See, the maximum file size is this. So what I'm saying here is that if your pointer, if it is depending on these two things, then I mean, if it is depending on number of pointers, so I will say that if the pointer size is less, then number of pointers will be more. Given that inode size is fixed, right, pointers will be more. You can actually store more pointers. So yes, size of the block, it definitely depend on size of the address. Size of the address means pointer. It depends on the pointer, yes, because it depends on number of pointers, and number of pointers and the pointer size is actually dependent. So a should be the correct answer. But let's just see if you have the stronger answer. So basically, if you see this option C, then option C includes the option A itself, right? Number of the blocks, size of the address block, size of the address block, and it also has one thing extra, which is saying the number of blocks used for the index. Yes, it depends on the inode size also, right? See, this number of pointers. Okay, I hope you are getting. See, the maximum file size is basically number of pointers into block size. And now if you calculate this number of pointers, that depends on inode size of inode upon pointer size. I mean, address size of address blocks, or something like that, right? So pointer size, right? So basically, ultimately, you get the file size that is depending on size of inode, size of pointer, size of the block, right? So it depends on the three things, and C has all of these three things. So C is the correct answer. A is partially correct, which means that A is not having all of this. A is just having two of them. B is also having just two of them, right? B is having number of blocks used for the index. B is having this thing and the size of the block, this thing, but it doesn't have the pointer. So A and B are the partially correct. These are not fully correct, which means C is the perfect answer that we have. So this is the formula that we have. And for this formula, it depends. Using this formula, you can say it depends on the three things. So that's why C is the correct answer, right? Yeah, so that's what it is given in the answer. But I think you can just modify this answer a little bit, in the little bit more better way. What you can do, you can just write these two equations, and then you can say that it depends on these three factors clearly, right? I'm not sure if they have done it in that way only. Number of address blocks, size of the block upon, okay, size of the inode. If that can be clear, the size of the inode, then it is better, right? So anyway, I think you can actually make this answer little more clear, right, in the comment section, or you can just pose your own answer. Okay, I hope you understood. Now let's solve more questions which have been asked in gate. So what they are saying, the data blocks of a very large file in the Unix file system are allocated using a data blocks of a very large file in the Unix. Okay, Unix is actually, I mean, that is some memory based question. So that is, I mean, I don't know, you can just remember it, this question. So Unix is basically using the variation of the index system, which is multi-level index, right? So this is just a memory based question, which is, you can say, multi-level index. So just see, continuous linked just index means only index, but if it is multi-level index, so you can say extension of index allocation, which is just a multi-level index, right? It is a memory based question. I mean, if you that is okay if you remember it. Otherwise, you have no option left. Okay. Yeah. So now let's solve this question. in a computer system, 4 files of this sizes, okay, 4 file sizes are given to us, and then they are saying for storing these files disk on the disk we can use either 100 byte disk block or 200 byte disk block. So they are saying these are the 4 sizes that I have, okay, 4 files that we want to store, and we have options. Either we can use 100 bytes or we can use 200 bytes, right? So the block size could be 100, and they are saying the block size could be 200 also, right? Okay, but can't mix both of them. For each block used to store a file, 4 bytes of bookkeeping information also needed uh, to store on the disk for each block used to store a file. So basically for each block you need 4 bytes extra information, right? For each block, for each, it's not just for the entire file, for each block 4 bytes metadata is also need to be stored, maybe some pointer to the block or whatever, right? 4 bytes metadata maybe, right? It seems like it is a fat table. I mean, I'm not sure actually, because metadata 4 bytes for each block, maybe because of the fat, in the fat we store metadata, right, for each block, maybe, I'm not sure. Let's just see. Thus, the total space used to store a file is the sum of the space taken to store the file and the sum of the space taken for the bookkeeping. Okay, so if I just ask you how much space this file is taking, so you will calculate how much space this file is taking. Is that how much space this file, because of the data it is taking this much, plus let's suppose it is actually using x number of blocks, then it is actually using 4x also, right? Why? Because for each block I'm using 4 bytes extra. So basically it will not just eat up that much space that is required actually, but it will also take, if you are going to store that in the in the x blocks, then 4x space it is going to take extra. That's what they are saying, right? I hope the question is clear to everyone. Now what they are saying is that, thus, okay, keeping the information, okay, a disk block can store either bookkeeping information for the file or the data from the file. Okay, so basically what they are saying is that in any block you can keep all the bookkeeping information, which means metadata, you can keep metadata, or in a block you can actually keep the file, but you can't do something like this, which means they are saying you can't store some metadata, some metadata or some part of the file in just one block. Okay, if you want to store, you have to use two blocks separately. Okay, what is the total space required for storing the files using the 100 byte and 200 bytes block respectively? Okay, let's just see using the 100 bytes. So using the 100 byte of block, how much blocks you need here, number of blocks for the file 1, equal to, you need to divide by 100. So I think 111 blocks you will be needing, right? Isn't it? Is this okay to everyone? You will be needing how many blocks? 11050 divided by 100. So you will be needing 111 blocks, right? And because of this 111 blocks, you have to actually, I mean, the total space will be taken this plus 4 into this. Okay, so anyway, I will calculate it. Let me just first calculate the number of blocks for the file 2. How much blocks you will be taking for the file 2? 4990 upon 100, it means 50 blocks you will be taking for the file 2. How much blocks you will be taking here? 52 blocks you will be taking. So 111, 50, 52, 127, right? These many blocks you will be taking. So that's why these many blocks into 4 also you will be doing to store the metadata, right? For every block you are going to spend the 4 bytes. So that's why total space taken using the 100 bytes will be sum of all of this, right? Sum of all of this. This is anyway you are going to take this much, 12640, sum of all of this, plus you also need to store this one. So 111 plus 50 plus 52 plus 127 into 4, right? You also need to store this one, so you need to add this one here. Let me know if that is fine to everyone. Okay. So that's how you can actually calculate using the 100 bytes, right? So what will the answer here? Do you want to calculate the answer? Let me just show you the answer actually. So 111 blocks required. So that's why this much extra. These many bytes you require extra for bookkeeping information. Another 5 disk blocks. Okay. So 111 blocks you require for this, and then you will be requiring, because of the 111 blocks you will be requiring, okay, you are calculating in terms of blocks, they are calculating in terms of blocks. So 111 blocks, okay, not in, I mean, you need to calculate in terms of blocks, yeah. So 111 blocks you need for the file only, and then what you need to do, apart from this 111 blocks, you need 444 bytes, which is equivalent to the 5 blocks. So basically, you just to store this file, you need 1116 blocks, right? 116 blocks. Similarly, just to store this file, you need these many blocks, like that, right? It is very aptitude kind of question. You can solve it. I hope that's fine. Okay. Moving further, in a file allocation system, which of the following allocation can be used if no external fragmentation is allowed? Where the external fragmentation is not allowed, I think in index you do not have any external fragmentation, right? Do you have the external fragmentation is contiguous? Tell me. Yes, right. In contiguous, we definitely have the external fragmentation, because we have seen this. If this is, let's suppose, occupied, this is occupied, then these two are giving you the external fragmentation. Linked, you do not have external fragmentation. In index also, you do not have. Wherever is the block, you can just pick it up, right? So that's why D is the correct answer. If external fragmentation is not allowed, then D is the correct answer. Okay. Now these kind of questions I think you can easily do. That is very easy question that is has been asking GATE 2019. So I think you can do it, right? Okay. Now let's see this question, what they are saying. Consider, I hope the question is visible to everyone, right? Now what they are saying, consider a linear list based directory implementation in a file system. Each directory is a list of nodes where each node contains a file name along with the file metadata. So they are saying the directory implementation of the file system, each directory is a list of nodes. Okay. So in each directory you have list of nodes where each node contains a file name along with the file metadata. So in each directory you have the directory means just a inode for the directory. Okay. Directory means inode for the directory. In each directory, or maybe inode of the directory, has the list of nodes where each node contains the file name, maybe let's suppose foo. Okay, it's here itself you are containing the file name along with the file metadata. Whatever is the metadata, maybe, okay, you are storing the metadata here itself, right? Whatever the metadata you are storing here itself, that's okay, right? So basically this is the inode of the directory, and generally we just call it just directory, such as list of the pointers to the data blocks and all, right? Whatever the list of the pointers, you are storing directly here. You are not maintaining the inode for the file separately. That's perfectly fine. Okay. Consider given directory foo. Suppose there is a directory. Okay. So suppose there is a directory which is foo. This is bar. This is, let's suppose, fee or something like that, right? Suppose there is a directory. This is foo. Now, which of the following will necessarily require a full scan of the foo for the successful completion? Creation of new file in foo. Do you require to look at all the files if you want to create a new file? What do you think? See, if you want to create a new file, then definitely yes, right? You need to check whether this file name already exists or not. So they are saying that will necessarily require a full scan. So I think A is the correct answer. But since this is MSQ, we will see if others are also correct answer, right? Okay. Deletion of existing file from the foo. Deletion, I don't think it requires, right? For the deletion, you can directly delete it. You do not need to look all of this. For deletion, you don't need. For, yeah, creation, you need. For renaming, yes, you need. It is. If you want to rename, then you need to check whether this exists or not, right? Opening, you do not need, right? So that's why A and C are the correct answer. Yes, Akash, that is correct. Okay. I think this is easy question that you can do, just like inode, triple inode and these kind of questions. Yeah. Now let's do this question which has been asked very recently, which is very good question. So let's just solve this question, which is one of the last question we are going to solve here. Okay. So what they're saying is that consider two file system A and B. What does this file system mean? File system means maybe the fat, maybe index, maybe contiguous, like that, right? These all are just file systems. So they are saying that two file system A and B that uses the contiguous allocation and the linked allocation. So there is A which is using contiguous allocation, and there is B which is using linked allocation. Okay. A file of size, a file of size a file of size 100 blocks is already stored in A and also in B. Okay. So there is a file that is taking 100 blocks that is stored in A, so which is obviously in the because of the contiguous allocation, it is stored contiguously, right? So suppose these are the 100 blocks that you have, and there is a file that is already stored in this 100 blocks. Similarly, here also there is a file that is stored in the 100 blocks, but because of the linked allocation, it will look something like this, right? Okay. I hope you got it, or maybe let me just draw this way. Right now, what they're saying, now consider inserting a new block of in the middle of the file between 50th and 51st block, whose data is already available in the memory. So there is a memory, okay, in this memory, main memory, in this memory some data is available. You want to write this data into one of the block, right, into one of the block, and basically that block should be, let's suppose this is the 50th block. Okay, so let's suppose this was the 50th block and this is 51st block. So you want to write that data into a block that is between this 50th and 51st block. Okay, so here also, and let's suppose this is the 50th block, so here also this is, let's suppose, 50th block. So you don't want to overwrite this 50th block, you want to write in between the 50th or 50th 51st block. Assume there are enough free blocks in the end of the file, so the control let the number of the disk access required to insert the block in A and B are NA and NB. So basically, let's suppose here if you want to insert a data in between, then you need NA access. Here you need NB access. Access means read and write access. So what they are saying is that how many read and write total you need in case of A, in case of B. So let's just first talk about in case of A. Okay, so A is basically saying that you have the contiguous allocation, right? You have the contiguous allocation and you want to store something here in between, right? You want to store something in the between. This is what it is saying. Now, can you tell me how many access you require? Access means read and write. Okay, I mean read is one access, write is one access. So you want to insert something here, right? And the data is already in the main memory. I mean, whatever you want to insert, that data is already in the main memory. What you will do, maybe okay, first tell me, you need to go here, I mean you need to first check that where you want to insert. So do you need to read it? I mean you will be reading it and then you will be going here, you will be reading it, going here, and then finally you go to the 50th block. Or since it is contiguous, I can directly go to the 50th block. Reading means, do you remember what do I mean by read and write? Reading means that if it is a main memory, then if it is a disk, reading means bringing something from here is called read. This is one IO operation, and writing something here, that is called write. That is another IO operation. Do you need to bring this in the main memory to just check what is the next thing? I don't think, right? I mean, you can directly go to the 50 because it's the contiguous allocation. You will do 50 into block size. Just by doing 50 into block size, something like that, you will be going here, right? And now you know where to write. So what you will do, you need to shift all of this. You need to shift all of this, right? Just one step here. So that is why you will be bringing this into the main memory. You will be bringing this in the main memory, and then you will be writing this to the next location, which is this. This is some new location, right? You will be writing this here, just bringing this in the main memory. This is one read operation. For this you are doing one read operation just to shift it, because you are bringing this in the main memory, and then you are writing it here. Oh sorry, you are writing it here, somewhere here. I mean, you might start from here, you might start doing it from here. So you will be bringing this in the main memory, you might start from here, and then this is one read you will be doing, and then you will be shifting it here. So one write, right? So basically there are total 50 blocks that you have that you have here, and then for these 50 blocks you need one read operation, you need one write operation. So total 100 operations you need for these 50 blocks. For these 50 blocks you don't need anything, right? And then once you do it, you need one more operation. See, once you do it, then it will look something like this. See, once you do once you shift all of them there, then it will look something like this. See, it will be something like, so which means that this was the early, like 50th one, this was the 50th one, earlier it was the 50th one. What you did, you have shifted the 51 block at the end. So this, sorry, 51 block at here. So this was, now this is 51, okay, and this is the empty, which means that it is not holding anything, it is empty. So after 100 operations, this is the case, right? After 100 read and write operations, so after 50 read plus 50 write operations, this is the condition that you have in the hard disk. Is this okay to everyone? Let me know, right? Okay. Now what you need to do, you need to write something here, because data is already available in the main memory. That's what they are saying. Data is already available in the main memory. You need to write that data here. So you do not need to read anything. You just need to write it here. So that's why you need one more operation to write it. So that's why NA is 101. NA means the number of operations you required just to write the data here. Let me know if that is fine to everyone. Right? Okay. Now let's go to the different case. So second case where you have the linked allocation. If you have linked allocation, then how this story is going to change? Let's just see. Okay. So suppose you have linked allocation and you want to basically, okay, you want to store something after it, right? Your data is already in the main memory. Then how much access you need? Your data is already here. Do you need to read it? To go here, can you just do 50 into block size or something, just like the same way we did earlier? No, right? We can't do like this. So basically you need to read it. You, after reading it, you will find that, okay, where is the next block where you want to go? Okay, next block is this, right? It is not continuous. It might be pointing to somewhere there, like that, right? So it need not to be continuous. So okay, after reading it, you will go here after, and then once you get the next block address, do you need to write it back or not? Tell me. You read it, that is okay, and then do you need to write it back? No, right? You have not modified anything. Why to write it back? I mean, there is nothing that you have modified, so no write, right? So you need to read it. So these are the 50 blocks. So you need 50 reads, 50 reads just to know that, okay, where to insert. Now you know that, okay, this is the address. I mean, it is pointing here. So after 50 reads, you know the address of this. Now what you will do, you will pick an empty block somewhere here. You will modify this 50th block, right? You will modify this 50th block pointer to here, and this block pointer to here, right? That's what you will do. So I mean, you will form a linked list. So after 50 read, let's suppose this is the pointer to next thing. So let's suppose this is this address is, let's suppose 100. Okay, I hope that is fine. So after 50 read, you know that you know this 100, right? Or maybe let me not confuse you. So after 50 read, basically you know the pointer to this. Now what you will do, you need 50 read operations, and then you need to modify this, right? So you need to basically what you will do, okay, there is some empty, this is some empty block somewhere in the hard disk. So what you will do, you will be do you need to read this empty block? No, right? I mean, there is nothing there, you do not need to read it. You need to write this empty block. How? You need to write this empty block with the data that you have, obviously with the data that you have in the main memory, with the data that you want to insert, plus one more thing, I mean that doesn't matter, but yeah, plus one more thing, this pointer, right? This pointer, so that it can point to here. So you need to write it. So 50 reads plus 1 write will give you this. 50 reads plus 1 write can give you this. Now it is pointing here, it is also pointing here, right? Now what you want this to point here, you want this to point here. I hope you are getting my point, right? See, 50 reads, you get the pointer to this, and then one write, in this one write, you write the data, you write this also, right? You do not need to read this empty block. That's important. You do not need to read, because this is some garbage. This is just empty block. Now, this is the situation currently. Now what you ultimately want, you want this pointer to modify this here also, right? That's what you want, which means that you need to write this also. You have read it, but you need to write this, you need to modify this pointer. So one more write you need for the 50th block, right? So total 52 IO operation you will be needing, 52 IO operation, sorry, 53 IO operation you will be needing. Earlier you need 101. Okay, so yeah, 153 is the answer. Sorry, this is 52. Yeah, this is 52 you will be needing. 52 IO operations you will be needing, and earlier you had 101. So that's why the total IO operation that you need is 101 plus 52, which is 153. Yeah. So is this okay to everyone? Like how we are calculating it? So A and B is coming out to be 52, and then finally you can just add them up, and then you will be having 53. 153. So yeah, that's all. And now we have one more question. So here you just had contiguous and linked, right? So we can do the same thing in case of index also, and not just the inserting in between. So this question is basically having different variations. Sorry, this one. So let me just remove this question. Yeah. So there is one question. This question is basically having different variations, which is that block not just in between. So we have just seen added in between, just one of the variation, which is this. So you may add at the beginning, you may add at the add at the end, you may remove from the beginning, you may remove from the middle, you may remove at the end. So there are 6 variations that you can have, and each of these 6 variations can be having 3 of this, whatever we have studied, 3 of the file system. So total 18 variations you can have. See, these are the 18 variations: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. So total 18 variations you can have like that, right? 3 file systems, and in each of the file system, beginning and middle or at the end, right? Insert or the remove. So that's why we have 18 different variations. So what you can do, you can try all of these variations, and I have the answers on the next page. Okay, if you want, you can try all of these variations. In the GATE 2022, they have just asked this variation. I think they have just asked these two. These two we have already done. Okay, but there could be 18 different variations like that, right? So I have taken this from one of the university, and I'm not sure if they have also taken from the same university. Okay, so they are just given one variation, but it is okay. If you have time, you can solve other variations also. Okay, so I think it is now time to wind up. So thank you everyone, and thank you so much for your time, your patience. Now we have completed the operating system. Most of the PYQs we have done. If there is some PYQs that we have not done, and you think that those PYQs should be solved, then please comment it out, those PYQs. Okay, if you comment it out, those PYQs, there's just a GATEOverflow link, then I will solve it in the next video. And one more thing, that if you like this session, if you like the all the efforts that we are putting, then please like the session and also comment that okay, you got everything that is explained in the lecture. Okay, so thank you everyone, thank you so much. Now the operating system is completed. Now we are going to start some new subject which will be computer networks, that will be from tomorrow. Thank you, take care, bye bye.